Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this lecture. In the previous lecture, we started studying modal analysis of multi-degree of freedom undamped systems, and we studied free vibration of multi-degree of freedom system, and we covered some important concepts like what is eigenvalue problem, what are natural frequencies, what are mode shapes, what are orthogonality properties, eigenvalues, eigenvectors, normalization of mode shapes, and so on. In this lecture today we are going to talk about force vibration of multi-degree of freedom undamped systems. So, today's topic is force vibration of undamped multi-degree of freedom systems. And specifically we are going to find the force vibration response to harmonic forces, okay, response to harmonic forces, okay, and then we are going to cover two methods. One is a direct method which is straightforward, and other is a method based on modal analysis, in which we will introduce some important concepts. So, let us consider a multi-degree of freedom system, and we have seen that the equations of motion for the multi-degree of freedom system, equations of motion for the multi-degree of freedom undamped system is mx double dot plus kx, and now we will have a vector of forces on the right hand side, right. So, here the matrix M and K, they are mass and stiffness matrices and they are symmetric. And why they are symmetric? They are symmetric because of the principle of reciprocity. Okay. So, and principle of reciprocity basically states that if we consider let us say load at point, let us say 1, right. If you apply force at point 1, at location 1, and if you measure the response, let us say static displacement at location 2, and let that location let that displacement be at location 2, okay. And now if you interchange the location of the force and displacement, that is, if you apply the force F at location 2, then it is seen that the displacement at location 1 is equal to delta, the same displacement. So, that is nothing but in short the principle of reciprocity, and because of this the mass and stiffness matrices, they are symmetric. Of course, we are assuming a linear system, right, they are symmetric for a linear system. So, that is the assumption, in fact, as we stated in one of the lectures earlier, that we are going to make that assumption in modal analysis, that all systems are linear. So, and then we are considering harmonic forces. So, let the harmonic force be given by f naught be the amplitude of the force vector, and let the frequency of force is omega. So, let us say f is equal to f naught cos omega t, and then we will use now method of complex exponential we studied earlier to solve the forced harmonic response, right. So, let us try to determine the response. The response would consist of the general solution would consist of two parts. X will be equal to the complementary part, and then we will have particular part of the response. So, let me represent total solution with x t, and let x c represent the complementary part of the solution, and x be the particular part or steady state part of the solution. So, let us focus our attention on finding the particular part of the solution, right, the steady state part or particular part of the solution, and later then we will add the complementary part to it to obtain the total solution. So, and now we are going to use the method of complex exponential to find the steady state part. So, this method we have discussed earlier. So, in this method we determine the response of the system to a complex force, say F bar t. So, let us say this is the complex force, and F naught e to the power I omega t, and we note that the actual force, which is F of t, is real part of this complex force. So, therefore, we determine response to F bar t, and then the actual response can be determined as real part of the response. Then we assume that let the complex response, the steady state response, is equal to say x naught e to the power I omega t. This is what we assume, right. And now we substitute these forces in the equation of motion, then what do you get? We get x naught minus omega square plus k x naught, right, e to the power I omega t is equal to f naught e to the power I omega t. Therefore, we can write the response as x naught is equal to k minus omega square m inverse of f naught, and the matrix k minus omega square m is called dynamic stiffness matrix. So, dynamic stiffness basically takes into account the effect of inertia of the system also, and this matrix is not constant, but a function of frequency. And then we can write the amplitude vector as alpha times f naught, and here the f naught, the matrix alpha, it's called frequency response function matrix. It's called frequency response function matrix. This matrix again is a function of frequency. So, if I write it alpha is a function of omega, then this is nothing but k minus omega square m inverse of this. So, this is one expression we get for the frequency response function matrix. And the reason it is a frequency response function matrix is because it relates the steady state amplitude of the displacement with the steady state amplitude of the force, harmonic force being applied on the system. So, this method of finding the response can also be referred as a direct method. Let us call it as direct method. So, in the direct method we directly solve the differential equation to find the response. Let us go to next page. Now, we are going to solve the equations by the procedure of modal analysis. Solution by modal analysis. In this procedure, what is done is that instead of solving the differential equations directly in the coordinate x, we first transform the equation to modal coordinates. So, let us try to see what this transformation to modal coordinates means. So, let us see what is meant by modal transformation. Every vector in n dimensional space, it can be represented as linear combination of basis vectors which span that n dimensional space. For example, if I have, let us say, 3-dimensional space like this, and any vector in this space, okay, it can be for example, if I take any vector like this, then this vector x can be represented as a linear combination of vectors which are the basis vectors. In this case, if I say this is the vector I, this is vector j and this is vector k, then I can represent this I j k vector as 1 0 0 plus x2 0 1 0 and x3 as 0 0 1. So, these 3 vectors which are basically these 3 orthogonal vectors, right, orthogonal vectors, okay. So, this one and this one, these 3 are orthogonal vectors and they form the basis vectors of this n dimensional space, because any point in this space can be expressed as a linear combination of these 3 vectors. So, x1, x2, x3 indicates the participation of each vector in the vector x. In the same way, there is something called modal transformation, in which the eigenvectors of the system, they are taken as the basis vectors. Okay. So, in modal transformation, the eigenvectors of the system, they are taken as the basis vectors, which means they are chosen as the vectors to expand the displacement vector x. And because the eigenvectors are basically linearly independent, right, and that is why they can be chosen or they qualify as an acceptable choice of the basis vectors, because the basis vectors are supposed to be linearly independent vectors spanning that space. So, therefore, we use the eigenvectors as the basis vectors in modal transformation, and therefore, the displacement vector x we obtain as linear combination of these vectors. So, if psi 1 is the first eigenvector and multiplied by y1 plus psi 2 y2 plus, for an n degree of freedom system, there will be n eigenvectors and n basis vectors are required. So, we have the n eigenvectors being combined linearly. to obtain the displacement vector. So, this also can be referred as an expansion theorem in terms of the eigenvectors. So, if you combine the eigenvectors together like this, with y1, y2 put into a form of vector like this, okay, then we can write this as eigenvector matrix psi multiplied by the vector y. So, this is the compact representation of the modal transformation, right. So, this is nothing but the modal transformation where the displacement vector of order n by 1, right, is transformed to a new vector y through eigenvector matrix n by, which is of order n by n. So, here basically y1, y2, y3 and yn, what do they represent? They represent the participation factors. So, y1, y2, yn, they represent the participation factors So, for example, YR represents the contribution of rth mode, okay, to the response x. Similarly, the Y1 represents the contribution of the first mode to the response x. That is why they are called as participation factors. They represent the degree of participation of each eigenvector in making up the response. So, we have the equation of motion m x double dot plus k x is equal to f, right, that is the equation of motion. And so, if now substitute x is equal to psi y, then I get y double dot plus k psi and y is equal to f. And then if we pre-multiply by transpose of psi, right, then we get psi transpose m y double dot plus psi transpose k psi y is equal to psi transpose f. And now, if you invoke the orthogonality properties, then psi transpose m psi, that is nothing but a diagonal matrix M R, and psi transpose K I is another diagonal matrix K R, and let us represent psi transpose F by say F R. So, what we see now, we have another set of differential equations, right. So, these are again n differential equations. So, we started with n differential equations and we again reached to another set of n differential equations, a new set of differential equations. But the important now difference is that this is the original set of differential equations, and this is where we now have transformed them to. So, these are also n differential equations. The difference is that the original differential equations, they were all in general coupled differential equations, right, and these differential equations, they are uncoupled, right, which means that they are independent. So, they are uncoupled because the matrices, coefficient matrices Mr and Kr, they are diagonal matrices, and hence the equations we got, they are uncoupled. So, each equation can be solved independently, but the original equations, the equations cannot be solved independently, they need to be solved simultaneously, right. So, they are coupled or dependent equations. So, that is the important advantage that is gained by modal transformation, that the equations of motion, they get decoupled, right, and each equation can be solved independently. So, if that is so, let us write one of these equations. So, if I look at say the rth differential equation, if I look at rth differential equation, then that I can write as Mr yr double dot plus Kr into Yr is equal to Fr, right. So, let us look at the rth differential equation. So, this differential equation seems similar to the equation of motion for the force vibration of a single degree of freedom system, right. So, if I look at a single degree of freedom system like this of mass m, stiffness k, and subjected to a force F, then the equation of motion for this system is simply say let us say if I consider q as the displacement coordinate, then m q double dot plus k q is equal to F. And now if you compare this rth differential equation with this differential equation of a single degree of freedom system, we see a great similarity. This equation looks very much similar to this equation, isn't it? And based on this, therefore, we can say that the rth differential equation, right, we have written here, which basically corresponds to rth mode, right. The in differential equations, they are in the because there are n number of participation factors y, and therefore, there are n number of differential equations. So, each differential equation corresponds to a mode of vibration. So, therefore, this rth differential equation essentially can be looked upon as the equation of motion of a hypothetical single degree of freedom system corresponding to rth mode. Okay. So, this differential equation can be looked upon as equation of motion of a hypothetical single degree of freedom system for rth mode of vibration of multi-degree of freedom system. So, this system, this equation or this differential equation basically describes the dynamics of rth mode of vibration of the system. And because we can look upon this as some sort of a hypothetical single degree of freedom system whose mass is Mr and Kr is the stiffness, and because they are related with a they correspond, this equation corresponds to a mode of vibration, these quantities we refer as modal mass and modal stiffness. So, therefore, Mr is called modal mass of rth mode and Kr is called the modal stiffness of the rth mode. And Fr is called modal force for the rth mode, right. So, but we should note that modal mass, modal stiffness, modal force, they are the mass, stiffness and force for a hypothetical single degree of freedom system, right, and corresponding to Rth mode. So, before we solve the Rh differential equation and other differential equations corresponding to all the modes, we can further give a physical interpretation to the responses we obtain from these differential equations. So, YR basically tells us the response in Rth mode of vibration, and that is why this is referred as modal response. So, if I have R is equal to 1, then I get Y1, and this will be the first modal response or response in the first mode. Similarly, R is equal to 2 would give me Y2, which would be the second modal response, and similarly if R is equal to N, I get Yn, which is the nth modal response. Or response in nth mode. So, therefore, based on this we now define what is called as modal space. So, modal space is the space spanned by the eigenvectors of the system, okay, is the space spanned by the eigenvectors of the system. And the participation of each eigenvector in making up the total response basically represents the modal response, right. So, therefore, each eigenvector is associated with a modal response. And the modal response of that mode and the eigenvector is together give the physical response corresponding to that mode of vibration. So, let us compare what we can call as the physical space, right, and modal space. Physical space and modal space. So, in the physical space we have let us first of all see the system. Let us take the example of a 3 degree of freedom system to understand this comparison. Let us say we have a mass here and then we have say spring here like this, and then we have another mass here, right, and then we have the spring here, another mass here and the spring here, right. So, you can see we have M1, M2 and M3, 3 masses, and then we have these stiffnesses K1, K2, K3, K4 and K5, right. So, this is the physical system. Actually we have a 3 degree of freedom system, and what are the degrees of freedom here? Say x1, x2 and this third mass has degree of freedom x3, right, and then you may have forces acting on it. So, let us say this is F1, F2 and on this mass you may have the force F3, isn't it? Now, for the therefore, this system which we call the system is in physical space, or the space spanned by the displacements x1, x2, x3, right. So, the coordinates are here, we have the DOFs are the physical coordinates, which are x1, x2 and x3, right. So, that is the physical coordinates. Maybe I can represent it by vector x transpose of this. So, these are the physical coordinates. Now, let us see what is there for the modal space. In the modal space, the system can be represented by 3 hypothetical single degree of freedom systems. So, I have this first system, then second system, and then the third system, like this. So, this first system has stiffness Kr1 and modal mass Mr1, and the force which is acting on this system is Fr1. Similarly, the second system has stiffness Kr2, mass Mr2, and force acting is Fr2, the modal force for mode 2, and then we have Kr3, Mr3 and Fr3. So, this first system with properties Kr1, Mr1 and Fr1, it corresponds to mode 1. It represents the participation of mode 1 in the response, right. It basically states the dynamic equilibrium, right, of the system in mode 1. This one is for mode 2 and this one is for mode 3. So, therefore, this space is described by modal responses by y1, y2, y3. So, this is the modal coordinates. So, these are called modal coordinates or modal responses, right. And this therefore, modal space is also referred as modal domain. So, that is one difference. Then the other thing is that the equations in the physical space, differential equations are coupled, right, while the differential equations in modal space are uncoupled. Another thing is that if I look at any particular coordinate, say xi, any physical coordinate, if I look at xi, this xi tells us the response, right, or physical response also we can call it, at ith DOF, right, and contains contribution of all modes, right. So, xi tells us the physical response at ith DOF, taking into account response due to all modes. The contribution of all modes is included in it. But if I look at the modal response, say y, say j, right, then it tells us the modal response or response in jth mode, right. It tells us the response in jth mode and gives the corresponding physical response right, which will be equal to what? Which will be equal to Yj times psi j, right, that will be the physical response equal to this. So, it gives the corresponding physical response at all DOFs, correct. So, that is another important difference, right. The the response xi gives us response at physical response at ith DOF and includes all the modes. It does not give response at other degrees of freedom. Yj gives the response in jth mode and tells us a response at all DOFs, but does not take into account the response of other modes, only the jth mode it gives information about. So, this is basically a brief comparison of physical space and modal space. So, this concept of modal space is very important for modal analysis. So, let us now go further and try to now determine the response, physical response of the system, because that is nothing but the objective of the analysis. So, if we look at the rth mode equation, if I look at rth mode equation, which is nothing but mr yr double dot plus kr yr is equal to fr. So, what is fr here? Fr is nothing but the dot product between the rth eigenvector and the force vector, right. And therefore, if I take the response to be if I take the force to be a complex exponential force, then the Fr can be written as psi r f naught e to the power I omega t, right. So, we have replaced here the f by f bar. So, if maybe we can just put an overbar over this to indicate that now we are using the complex exponential force. So, if that is the case, then Fr would be psi r transpose f naught e to the power I omega t, and therefore, this quantity I can call as Fro, the amplitude of the rth modal force. Oh, I think this is a scalar, so I think we can just write it as Fro. So, therefore, Fro is nothing but Fro, which is the amplitude, it is nothing but psi r transpose f naught. So, Fro is nothing but the dot product between the rth eigenvector and the amplitude of the force vector, right, the harmonic force vector. Now, if you substitute, so now let us also assume yr also to be harmonic I omega t, right. So, if you substitute these two equations in the differential equation, what we get is minus omega square mr yro plus kr yro is equal to Fro, and we get Fro yro as Fro upon kr minus omega square mr. So, that has basically gives us the amplitude of the modal response of rth mode. So, if I multiply by e to the power I omega t, or if I substitute Fr naught here, then what do I get? I get psi r transpose f naught divided by kr minus omega square mr, right. And therefore, so now we can obtain the physical response. So, this is nothing but the amplitude of the modal response, and if we like, we can also substitute this in this equation to obtain the YR, which is psi r transpose F naught upon Kr minus omega square mr. So, now we can obtain response in physical space. Right, response in physical coordinates, and now we can substitute this modal response in the modal transformation equation, and that equation is x is equal to psi y, right. We can also expand it and write down psi r y r, with r varying from 1 to infinity. So, if we substitute equation for y r, then we get psi r y r is now psi r transpose F naught upon K r minus omega square m r, with r varying from 1 to n. And now, if I divide the numerator and denominator by square root of m r, right. So, this is the equation in terms of the eigenvectors psi, and they and yet we have not considered any particular normalization scheme for the eigenvectors. But if we can rewrite this equation or convert this equation in terms of the mass normalized eigenvectors, right, by replacing these eigenvectors by mass normalized eigenvectors. So, let us divide the numerator and denominator by square root of m r. So, we get, let us rewrite that equation, psi r transpose K r minus omega square m r, with r varying from 1 to n. So, here we do not have to divide by square root of m r, but m r itself. Okay. So, if we do that, then what do you get? Let us write this as m r square root of m r square root of m r, okay, and then in the denominator we have K r upon m r minus omega square, and we can take F naught vector outside, because that is anyway a vector of constant, it does not depend on the mode r, index r. So, with r varying from 1 to n. So, now this quantity is nothing but the mass normalized eigenvector phi r, right. So, this is nothing but phi r transpose divided by K r upon omega r is nothing but omega r square, that is the rth natural frequency, minus omega square, and this is nothing but x. So, I think another we can just go back to previous page. So, here I think we have missed the e to the power I omega t term, right, because when we make a substitution for y r, we have just substituted y r naught, but we have missed e to the power I omega t, right. So, therefore, we will have e to the power I omega t here, okay, and therefore, this quantity, okay, this can be written as this can be written as x naught e to the power I omega t, right. So, therefore, we get x naught from here, which is summation of product of phi r transpose divided by omega r square minus omega square with r ranging from 1 to n multiplied by f naught. So, this is nothing but the steady state response amplitude. This is the steady state response amplitude. So, this basically forms a particular part of the solution, right. So, now we find a complementary part, right, complementary part. The complementary part is the solution of the corresponding homogeneous equation. So, the corresponding homogeneous equation for the differential equation of the system is mx double dot plus kx is equal to 0, right. And already we have obtained a general solution of this homogeneous equation in the previous lecture. So, we can combine that with the steady state solution to obtain the total solution. So, the complete solution, which consists of the complementary part and the particular part, can be written as, so xc would be now a linear combination of the free vibration solution consists of the linear combination of vibration in various modes. So, if say ai say phi I, if I take as the mass noise eigenvector cos omega I t plus b I phi I sin omega I t, right, varying from 1 to n, plus now we got the particular part of the solution, which is nothing but and then we also need to take the real part of it, because the solution we obtained is for the complex exponential force, while the actual force was simply the real part of that. Hence, we write down the steady state part as psi r transpose divided by omega r square minus omega square, right, into f naught cos omega t. So, this is nothing but the complete solution, and in this solution a I and b I, they are arbitrary constants. And they are to be found from initial conditions on the state of the system. Okay. So, once the initial conditions like the initial displacement vector and initial velocity vector are given, we can obtain ai and bi from here, because those would be 2n number of conditions, and then there are 2n number of unknowns, and these equations can be solved. So, this is nothing but the forced harmonic response of the multi-degree of freedom system. Let us go to the next page. Let us define now the what is called as spatial model of the system, right. We saw that the response, the dynamic response of the system could be found out if the mass matrix and stiffness matrix of the system are given, right. So, by solving the differential equations in physical coordinates, the response x can be obtained. The response x can be obtained. And these equations, they require the knowledge of the mass and stiffness matrix to perform an undamped analysis, right, to solve the response based on the undamped model. So, knowledge of mass and stiffness matrix is required. So, if this is available, then we can find the response to the given excitation force, and that is why the mass and stiffness matrix together is referred as a model of the system. They make up a model of the system, and this model is called spatial model, right. So, M and K, they together make up what is called as spatial model of the undamped system. So, if there is a vibrating system, the mass and stiffness matrix of the system together make up the spatial model of the system, right. And of course, it's a because as we said earlier, the models are not unique. It forms one of the models, one of the spatial models of the system. So, if this is given, then we can obtain. So, if I am given the spatial model in terms of the mass and stiffness and mass matrix, right. So, that basically is the model, and then if we are given the excitation forces acting on the system, then we can solve using this model the output of the system or the output response of the system that can be obtained. Then there is also something called modal model. We also saw that if the eigenvalues and eigenvectors of the system are available, right, then the response of the system can be found for a given excitation force, right. So, if eigenvalues and eigenvectors are there, we can find the response of the system if the excitation force and initial conditions are given. So, therefore, the eigenvalues if we put them in the form of a matrix, diagonal matrix, then it would be something like this. We will have omega 1 square, omega 2 square, omega n square. So, these are the eigenvalues on the diagonal. So, this matrix is an n by n diagonal matrix, and this we call as the eigenvalue matrix. Similarly, we have the eigenvectors, which is in the form of the mass normalized eigenvectors. So, here each column of this matrix is a mass normalized eigenvector of the system. And this is nothing but the eigenvector matrix. So, if these two matrices are available, then also we can analyze the system for its response, right, and therefore, these two together make up what is called as modal model of the system. Okay. So, therefore, we can represent the relationship using this simple block diagram and say that if I have the model, I can find a dynamic response for the given excitation force, and this model it consists of the eigenvalue matrix and a mass normalized eigenvector matrix, right. This is the model model. So, these are the two equivalent descriptions of the system. If either of them is available, it is possible to do analyze the system for its dynamic response. Now, for a single degree of freedom system, we have defined frequency response function. Let us try to define frequency response function for a multi-degree of freedom system. And for a multi-degree of freedom system, the FRF takes the form of a matrix, right. So, for a multi-degree, for a NDF multi-degree of freedom system, there are n number of degrees of freedom at which responses can be measured, right. Similarly, n DOFs are there where forces can be applied. So, therefore, we can have several combinations of the response and force coordinates corresponding to which the frequency response function can be defined, right. And that is why we have since we have n response coordinates, right, and then there are n coordinates possible for force. So, that is why there are n into n, that is n square number of combinations of response and force coordinates, and hence there are n square number of FRFs, n square number of frequency response functions corresponding to each choice of response and force coordinate. So, therefore, we have what is called as the frequency response function matrix, right, and that matrix is written in this form: alpha 1 1, alpha 1 2, going up to alpha 1 n, then alpha 2 1, alpha 2 2, going up to alpha 2 n, and then we can have alpha n 1, alpha n 2, going up to alpha n n, right. So, therefore, we have a n by n FRF matrix. Now, if I look at any one of these FRFs, say alpha j k, then what does alpha j k represent? So, what is FRF alpha j k, right, alpha j k. So, alpha j k, which of course is a function of omega, it depends on what frequency is there. So, alpha j k omega is the ratio of the steady state amplitude at jth degree of freedom divided by the harmonic force amplitude f k at frequency omega, right. So, it is the ratio of steady state amplitude at jth degree of freedom to the harmonic force amplitude at kth degree of freedom, the force applied at kth degree of freedom, and the force at any other degrees of freedom, right. The force at any other degree of freedom should be 0, right, for q not equal to k, right. So, it is for all q, f q should be 0 for all q except q is equal to k. So, let me rewrite that, except q is equal to k. So, it means the force is applied only at kth degree of freedom, a harmonic force with frequency omega is applied at kth degree of freedom, and then the response it causes at the jth degree of freedom, the amplitude of that response divided by the amplitude of the force at kth degree of freedom, this ratio basically is called the frequency response function. So, this FRF matrix is symmetric. That is another important property of this matrix, right. FRF matrix is symmetric for a linear system. Since the modal analysis theory is based on the assumption of linearity, so we would always assume that the FRF matrix is symmetric. So now we can this FRF matrix. What is FRF? Let us try to determine that. So for a multi-degree of freedom system, let us determine the FRF matrix. So if we look at the expression we got for the steady state response amplitude, let us write that expression again. That expression was phi r transpose divided by omega r square minus omega square f naught, isn't it? So now let us see, let us say we want to find out what is FRF alpha jk. Can we identify the alpha jk from this expression? Principally it should be possible, because we are applying a harmonic force whose amplitude is vector f naught, and we obtained a steady state response to this harmonic force vector. So from this expression it should be possible to determine alpha jk. So let us invoke the definition of alpha jk we just defined. So let us have a unit amplitude harmonic force at kth df, right, and no force at all other dfs. If that is so, then what will be f naught? F naught would be simply 0 0, and then we will have unity, and then 0 0 all this. So at the kth df we have the unity, while at the rest of the df the force amplitude is 0, and this is a vector n by 1. So when we substitute this in this equation, what is going to be the result? The result would be let us write this here, or maybe okay, x naught is equal to summation phi r. So now phi r transpose vector f naught, that would basically lead to only the kth term of the rth mode here, right. So we will simply have phi k r, omega r square minus omega square, with r varying from 1 to n. So this gives us the response at all the n dfs, but our interest lies in knowing the steady state response amplitude at only the jth df. So therefore we need to just pick the jth element of this vector x naught in order to find the FRF, right. So this we can just find out the response at jth df, and that would be simply x naught j, and that would be nothing but f alpha jk, and we get from here alpha phi j r, right. So only the jth element of the eigenvector rth eigenvector will be remaining here, right. So we get k r phi j r phi k r omega r square minus omega square, r varying from 1 to n. So, in this way you can see we got this expression for the FRF alpha j k. And therefore, this is a very important expression. It says that the FRF basically is dependent on the eigenvalues and eigenvectors. So, if eigenvalues and eigenvectors are there, then the FRF can be determined. So, it gives a relationship between that. And also if so what is the FRF matrix? So, if you compare the expression we just wrote for the steady state amplitude, then with the expression we got earlier, we got this expression, right, between the x naught and f naught. So, when we solved the force response amplitude using direct method, this is the expression we got. And if we compare this equation with the equation we just wrote previously, then we can directly write down the matrix alpha here as phi r transpose omega r square minus omega square with n r varying from 1 to n. So, this is nothing but the expression for the full FRF matrix, right, it is for the FRF matrix, right. So, this shows that the FRFs are related with the properties of the modal model. It gives us the relationship between the modal model and the FRFs. And we earlier also saw the relationship between the FRF and the spatial model, because we saw that FRF matrix alpha is equal to k minus omega square m inverse. So, that is nothing but a relationship between the FRF and the spatial model. So, therefore, we can say that if I have the frequency response functions, then it is possible to find out the response, and hence we define another model, another type of model of the system, response model. Okay. And this we are going to define in the frequency domain. It is a frequency domain response model, because we just saw that the FRFs can be used to find the response. So, let us say we have the forces acting say F the force vector of harmonic forces acting, and let us say this is nothing but F naught 1, F naught 2, F naught 3, right, like this, e to the power I omega t. Let us say this is the vector of forces acting, right. Then how do you find out the response if based on the FRFs? So, let us say I am interested to find the response at jth DOF, right, when all these forces are acting, the force vector is there. So, then I write down x j, right, and this of course is at certain frequency omega. This is equal to now the response due to the force at the first degree of freedom, and that can be obtained by multiplying the FRF alpha j1 with the amplitude of the force at first degree of freedom, right. So, this is at frequency omega. Then there is also response due to FRF, response due to the force at the second degree of freedom, and that can be obtained by multiplying the FRF at jth degree of freedom due to force at second degree of freedom multiplied by the amplitude of the force at the second degree of freedom, plus in this way I need to add response due to other forces also, right. So, acting at other DFs also. So, let us say response due to the force at the nth DF would be alpha j n multiplied by f naught n omega. So, you can see in this manner if I know these FRFs, then for the given excitation I can determine the response, and therefore, the response availability of FRFs also constitutes a model of the system. Okay. So, the FRF matrix constitutes response model of the system in the frequency domain. So, therefore, in summary, there are three types of representations of the system possible. One could be the spatial model representation based on the mass and stiffness matrices for an n-dimensional system. Then we can have the modal model based on the eigenvalues and eigenvector matrices of the system, and then we can also have a response model in the frequency domain defined by the FRF matrix of the system. These three representations or model descriptions are equivalent, and and they basically all allow us to determine the response of the system to any dynamic force acting on the system. So, in this way today we looked at the forced vibration of the multi-degree of freedom system, and we also developed an important concept about the modal space when we looked at the response analysis using modal analysis. So, I think we can stop here. We will continue in the next lecture. Thank you.